Hello, good morning. Today we are taking the topic method of solving system of linear equations, and I will take you through all the various subtopics under this very big topic. First of all, we will consider the direct methods, which is mainly the Gaussian elimination and the LU decompositions. Under Gaussian elimination, we will look at the partial pivoting and scale pivoting as well. Then under LU decomposition, we are going to discuss the Doolittle method, the Crowd's method, and the Koleski decomposition. Then we end this topic with the iterative methods of solving system of linear equations, where we will discuss the Jacobi method, the Gauss-Seidel, and successive over-relaxation method. First of all, let me take you through some basic linear algebra, some of the things that you learned in linear algebra. What you see on your screen is a linear system of equations, a system of linear equations, and it comprises n variables and m equations. And as you were told, this system is called a homogeneous system if all the values of the b, which is the right-hand side values, are all equal to 0. And it is called non-homogeneous when not all the bi's or the right-hand side values are 0. The system can be written in the matrix form where we have AX is equal to B, where the A is the coefficient matrix, the X is the vector of variables or unknowns, and B is the vector of right-hand side values. It can also be put in the augmented matrix form, where you augment the coefficient matrix and the right-hand side values or vector of the right-hand side values to form this. So from the system I showed you, this would be the augmented matrix. Taking an example as this one, what you see on your screen, we can form this particular or rewrite this system of linear equations into the matrix notation, which gives this matrix a matrix of 2, 1, negative 1, 1, negative 2, 0, 0, 4, 2, and the vector is x1, x2, x3, that's the vector of unknown, and the vector of right-hand side values 2, 3, 1. In augmented form, we have our system put in the form as you see on your screen. Some basic definitions that we might need. The rank of a matrix. As you learned in the linear algebra, you were told that it is the number of linearly independent rows in any given matrix or in that particular given matrix. Or it can also be defined as the number of non-zero rows in the row-reduced form of the given matrix. So looking at the example we have on your screen, this particular example gives the first 2 rows of this particular example are dependent on each other. Because if I multiply row 1 by negative 1, I'll get the row 2. And row 2 by negative 1 gives me row 1. So it means the row 1 and row 2 are linearly dependent. So as you learned in linear algebra, counting linearly independent rows, you have to first of all look for all the linearly dependent rows and put them together as one. What that means is that the set of linearly dependent rows are represented by just one of the rows. So row 1 and row 2 can be represented by just one of them. And so we say that we have row 1 and row 2 to put together as one. You count row 2 row 3 in addition, making it 2, and then row 4 comes in as the third row. So in all, we have the first 2 being linearly dependent rows, and for that matter, there are 3 linearly independent rows, and the rank of the matrix is 3. If I go through the Gaussian elimination to eliminate or to reduce the matrix into its row echelon form, this is what you get. What you see on the screen is what you get. And this particular, the second definition says that it is the number of non-zero rows in the row reduced form of the matrix. So if this is the row reduced form, then how many of these rows are non-zero? Remember, when we say a zero row, we are talking about a row that is completely zero. So all entries on that row is 0, and that's the only 0 row in this particular matrix is the 4th row. And for that matter, the number of non-zero rows gives us 3. So there are 3 non-zero rows, and that we can say that the rank of the matrix once again is equal to 3. So having these definitions right, we can now move to what is called the elementary row operations for Gaussian elimination. There are 3 main row operations for solving system of linear equations. The row replacement, which replaces a row by a sum of itself and a multiple of the other or another. Row interchange, where we can interchange 2 rows, and row scaling, where we multiply a row by a non-zero constant of that a non-zero constant. So these are the 3 main known operations under elementary row operation, or what is Gaussian elimination. And what I want to emphasize here is that look at the definition of the first operation. It says that you replace the given row, the row that you want to replace, you replace it by a sum of itself and a multiple of another. In this particular case, the multiple we are talking about here is what we call the Gaussian factors. And so it is going to be the sum of itself and a multiple, which is the negative of the Gaussian factors. In this case, gives us the multiplier. And that is what we are going to use to replace the matrix or the given row. So I'm going to start with this particular example we have on the board, and I'm going to explain all the 3 steps that we have defined over there. But permit me to say that under linear algebra, you were doing all these 3, the row replacement, row interchange, and scaling. But under numerical methods, scaling is actually not necessary, and I don't accept scaling under numerical methods. The reason is that the idea behind numerical methods is to solve the system of linear equations using computers or programming. And computers do not care whether the pivot is a fraction or it is a whole number. The whole idea behind scaling is for human to get a non-fractional value as your pivot to work with. I'm very sure you remember that under linear algebra. It is when you have a fraction as your pivot that you were multiplying through by a certain constant to make the pivot a whole number so that you proceed. So under linear algebra, we were doing scaling, row scaling, but in numerical methods, we will not do scaling. Again, very soon you would understand why scaling is not necessary, because the idea behind numerical methods is to be able to code the operation. And whenever you scale, if you are not careful, you might not understand the real operations of Gaussian elimination, and your program might not be correct. So I'm going to go through the Gaussian elimination without the 3rd operation, scaling will not be used. I'm going to use only row replacement and where necessary, row interchange. And once again, get the definition of the row replacement. It is replace the row by a sum of itself and a multiple of another. And the multiplier here, I'm talking about what the Gaussian factors, which I will introduce to you very soon. Those of you who are not familiar with that. Let me use this example to explain the Gaussian elimination. And the example, as you see, is given by it's given by 2, 1, minus 1, 2. I have 1 minus 2, 0, 3, then 0, 4, 2, 1. This is the system in augmented form, and we want to solve the system using Gaussian elimination. So as you are aware, we need to just do row replacement of the second row. And the idea is to make the one here go to 0. So I have this as 2, 1, minus 1, 2. So I have to put this particular, I need to replace the row 2 with a new form of row 2, where the first entry in row 2 has been changed to 0 through mathematical row operations. So let's look at how to do this. We're going to have it as row 2, the new one is actually equal to the old row 2 minus the Gaussian factor times the pivot row, which is row 1. So what is this Gaussian factor? The Gaussian factor is computed as the number to send to go to 0, the number that you are sending to go to 0, this particular number that you want to take to 0, divided by the pivot at that particular stage, which is the 2. So my Gaussian factor in this case is given by 1 over 2. I am going to be strict on the use of this operation because I do not accept the other way of elimination, which some of you are familiar with in some other books or some other course. The reason is that that particular way of reducing the row, to me, to the best of my knowledge, will not help us in linear algebra. And I can even say that it is not Gaussian elimination. So I don't accept the idea of swapping these entries, multiply row 2 by 2 and row 1 by 1, and then you subtract. So I don't accept this particular operation that we do. Row 2 minus, so 2 times row 2 minus row 1. I will not accept this particular operation because it has some issues. Here, permit me to restrict you to the use of Gaussian factors because we will need the Gaussian factors in other operations or in other studies. Again, this particular way of reducing your rows have some issues which I'll discuss with you briefly. If you go by this, it defeats the process or the procedure for Gaussian elimination, which states that when your pivot is 0, the Gaussian elimination must not work. But this particular operation, I can show you that even when the pivot is 0, by this means of elimination, you can proceed to eliminate all the entries below the 0 to go to 0. Let me maybe digress a little and then show you why I don't accept this particular way of Gaussian elimination. It is assuming I have this matrix and my matrix is 0, 1, 2, and I have another matrix, another row 2, 1, maybe 1. Then I have 3, 1, 2. This is my matrix. I want to reduce this matrix using the operations that you sometimes use. What is going to happen is that I'll keep my row 1, 0, 1, and 2. Then I want to reduce this row to send this entry to go to 0. What you are going to do is that it is going to be row 2 minus, is going to be 0 times row 2 minus 2 times row 1. So when you do this, because I'm swapping the 0 and this guy, when I do that, I'm going to get 0, 0, 0 minus 2 times row 1 will give me 0, 2, 4. When you subtract, you're going to have 0, negative 2, negative 4. So eventually, we have succeeded in eliminating the entry below the 0 without any difficulty. In the same way, you can eliminate this entry 3 without encountering any problem. And that will end up giving you 0, negative 3, negative what? 6 by 0 root 3 minus 3 times root 1. So you see, this kind of elimination will allow you to even proceed with the elimination even when the pivot is 0. But that is not what we know about Gaussian elimination. The Gaussian elimination is supposed to break when the pivot is 0. So now, let me go to the Gaussian elimination procedure that I wrote earlier, this particular one, and then try to apply that particular one here, and you see what will happen. So now, if I want to eliminate the second rule, I want to eliminate the second rule. This time, I am going to write it as what? I'm going to write it as row 2 minus the Gaussian factor times row 1. And what is this Gaussian factor? I told you that the Gaussian factor is computed from the entry that must go to 0, which in this case is this particular entry. This entry that must go to 0 divided by the pivot. So it is going to give us 2 divided by 0. Immediately you get this, it tells you that Gaussian elimination cannot work because you cannot compute the Gaussian factor, which is 2 divided by 0. And that tells you now Gaussian elimination will break. But in the previous elimination that you were doing, where you swap 2 entries to multiply row 1 by a certain number and row 2 by a certain number, there is nothing mathematically that can cause that particular elimination to stop when the pivot is 0. So again, I repeat, I will not accept that kind of elimination in numerical methods, and we are not going to use that. So now that we are clear about the use of the Gaussian factors, let's proceed with our Gaussian elimination. And then I will again tell you why we don't need scaling as well in numerical methods. So now this particular procedure is not going to be used. So we are going to use our Gaussian factors which in this case, using this particular equation is going to give us row 2 minus half row 1. And that is what we are going to use. And in this case, what do we have? Let me quickly write that somewhere. Row 2 is 1 minus 2, 0, 3. And half times row 1 will give me 1 here, 1 over 2, minus 1 over 2, and then what? 1. Then I'm subtracting. So when I do that, I'm going to get here to be 0. This will give me negative 5 over 2. This will give me positive half, and this will give me 2. So in effect, I'm putting in place of row 2, 0, negative 5 over 2, 1 over 2, and then what? 2. So that is our new rule. I'm very sure now you can actually predict or tell me the operation at row 3, and it is row 3 is equal to the old row 3 minus, what is the Gaussian factor now? The Gaussian factor is 0 divided by 2. So let me write it as 0 over 2 row 1, because it is row 1 is still our pivot row. And when we go through this, everybody agrees that it will be the same as the row 3, as 0, 4, and then 2, 1. So this is what we have as the first iteration of Gaussian elimination. I know usually at this stage, what is our new pivot? The new pivot is formed by eliminating row 1 and column 1. Then you pick the left top corner entry as your new pivot. And so this becomes our new pivot. 5 over 2 becomes our new pivot. And it should help us to reduce the 4 below it to go to 0. So this is equivalent to, so the new row, so we keep our row 1, which is 2, 1, negative 1, 2, and keep our row 2, which is our current pivot row, minus 5 over 2, 1 over 2, and 2. And then now we are going to reduce the row 3. I know in linear algebra or in some courses, you would have started scaling your row 2 because the pivot is a fraction. And as I said, in numerical methods, we don't need any whole number because computers don't fear fractions. They can solve any given problem even when the pivot is a fraction. So we are going to proceed. And then I will also tell you again, another reason why we don't need the scaling, because it is confusing. It makes you think that the number of iterations you have used in the Gaussian elimination is more than what you actually need. So I will explain those concepts a little bit very soon, and you'll see the reason behind why we are not going to use the scaling. So in row 3, now our row 3 is actually equal to the old row 3 minus, what is the Gaussian factor at this stage? It is going to be 4 divided by negative 5 on 2. That will give us negative 8 on 2. So, sorry, negative 8 on 5. Negative 8 on 5. Negative 8 on 5. So with negative 8 on 5, we have it as negative 8 on 5, row 2, which is our pivot row. So what do we get by that simplification? We are going to have it as So let me do that computation somewhere. My root 3 is 0, 4, 2, 1. When I multiply -8 on 5 by the root 2, I'm going to get 0, 4 here. -8 on 5 by that will give me -8 on 5 by that will give me what? -4 on 5. And then by this will give me -16 on 5. And so we subtract. And when you subtract, you're going to have 0, 0. This will give us is a 14, positive 14 on 5. And this will give us positive 21. So in effect, what we're going to put here is 0, 0, 14 on 5, and 21 on 5. So this is what we have as the last operation under this elimination, because the next pivot is to delete row 1, row 2, column 1, column 2, and then the next pivot will be 14 on 5. But since there is no entry below 14 on 5 to reduce to go to 0, we leave it as it is, and then that becomes the last operation. So this is our Gaussian elimination, and very soon you will just proceed to solve the system using the back substitution, where you write this particular matrix back into the component equation form and then solve each of the entries of X using the back substitution. But before we go there, let me open up to you some of the properties of this Gaussian elimination we have seen so far. Because we have 3 linearly independent equations and 3 unknowns, 3 linearly independent equations and 3 unknowns, it means that our system has a solution, and the solution is unique. And if the solution is unique, then you need the number of iterations to achieve your reduced form must be 1 less than the number of rows or the number of independent rows you have in the operation. So the number of iterations you need to solve the system is 1 less than the number of independent rows you have in the system. So in our system, we have 3 independent rows, 1, 2, and 3. So how many iterations do we need? Strictly 12, simply 2 iterations. Iteration number 1 is this one, and iteration number 2 is this. You see, the reason why I left this particular space here is that I want to show you what you would have written before this particular system if you were scaling. If you were scaling or if scaling is allowed, I'm very sure you would have written over here that this is equivalent to 2, 1, minus 1, 2, and then multiply your row 2 by maybe 2 to get 0, minus 5, 1, and then what? 4. Then you have 0, 4, 2, 1. You see, with this particular operation in between the actual first iteration and the second iteration, you might think that you have used 3 different iterations. But this particular step, as I told you, is not a Gaussian elimination step. It is a step that is only helping us as humans to be able to do our operations easily without any difficulty. But it is not a Gaussian elimination step that without it, we will not get our correct answer. So this is not an iterative step. The only iterative steps are this one and that one. So if you write this particular one, you might be confused to think that you have used 3 iterations, but in actual fact, they are only 2 iterations. And so, once again, scaling is not allowed so that we don't get confused of the number of iterations that we have used. So, I don't need this particular step to be part of my solution procedure because I want to see the real iterations and get my answer exactly as it should be. So this is the Gaussian elimination method, and this is what we're going to use as Gaussian elimination. We will discuss the whole procedure in detail so that you can actually code the procedure in maybe MATLAB or any comfortable environment for use. So this, what you see now, is the Gaussian elimination. I will take you through some of the properties of the Gaussian elimination, what that we have done up to this point. And these are the properties. Property number 1. Property number 1. We have the number of iterations used is less than the number of linearly independent rows by 1. So assuming I want to code this particular method, look at what I'm going to have. I need to know the number of linearly independent rows or the number of rows of the system. And that is going to give us n is equal to, maybe in MATLAB, we can use the length of vector b. The length of vector b will be okay. Somebody can also say that I'm going to set n, m equal to the size of the matrix A. So in this, you have n being the number of rows and m being the number of columns. So in both cases, we have the value of n. And then we'll enter, of course, we have to input, we should have input A and input B. So we have input A and input B. Then your n is equal to the length of B, or you can set n and m to be equal to the size of A, where again you will get the n to be equal to the number of rows of matrix A. So now we need to discuss the whole procedure. So first of all, you need to set the number of iterations that we are using. The number of iterations that we are using is going to be, because we are talking about iterations, so obviously it's kind of a loop. So I can use any loop that will capture my iteration. So the for loop will be okay. So I can say that for I running from 1 up to where? N minus 1. Because we have all agreed that if my number of linearly independent rows is n, then I'm going to do n minus 1 iterations. When we had three linearly independent rows, we use 2 iterations. So when we have 4 with 4 unknowns, we are going to do 4 iterations. Sorry, 3 iterations. And so it is going to be 1 less than the number of equations or the number of rows. So I can say that I end my iterations, the iteration loop over here. So it is 4 to an end, like that. Then, when I'm in iterations, you ask yourself, in any given iteration, how many different rows changed? So when I'm in iteration 1, I change the entries in row 2, and I change the entries in row 3. So I believe that you are getting the picture that when I'm in iteration 1, I started the changing of rows from row 2. When I got to the iteration 2, the only row that changed is the row 3. So look at the, I hope you see the link. Iteration 1 starts from row 2 all the way to row 3. Iteration 2, you start from row 3 all the way to row 3, which is the last. So what does that tell us? It tells us that for the iteration loop, for the rows loop, the rows within which we are going to work, if we say it is J, then J starts from where? Somebody will say 2, but you can smartly see that iteration 1, we are starting from row 2. Iteration 2, we are starting from row 3. So if I know the index for the row, I can just say that it is the row plus 1, the iteration plus 1 all the way to n. So you see, for iteration 1, I'm starting from 2. Iteration 2, I'm starting from 3. And so if I'm in iteration 1, I'm going iteration I'll start from where? I plus 1 to n. And then we end that particular loop as well. Then, now you have to decide how you are going to do the elimination. We know the iteration, I'm in iteration 1. I know the row that I'm going to change, and then what is the operation going to be? The operation, I need a certain number called the Gaussian factor to be able to do the operation. So how do I compute my Gaussian factor? The Gaussian factors, if you have followed the discussion, you would realize that if I have a general matrix A11, A12, A13, I have A21, A22, A23, and then A31, A32, A33. Then the first Gaussian factor I computed, which came from the entry here, this entry divided by the entry here, this entry divided by this one, is going to be what? A21 divided by A11. So my first Gaussian factor, which is related to this guy, came from A21 divided by A11. Is that okay? In this particular case, at that particular point when I was computing the Gaussian factors, I only knew the iteration within which I was working, and I knew that I'm working in row 2. Get the statement again. I'm working in iteration 1, row 2, and look at the indices of the entries that I'm using. A21, A11, iteration 1, row 2, and the indices are 2, 1, 1, 1. So I hope that actually gives you a clue of where the 2 and the 1s are coming from. So it should tell you that before I started the elimination, I only knew the row with the iteration within which I'm working and the row within which I was going to work. And my Gaussian factor was this. You can compute the other Gaussian factor for the second row, the third row. And this time, what did we use? We used A31 divided by A11. Again, this place, we knew you were working in iteration 1 and row 3. And look at the indices, 3, 1, 1, 1. So what does that tell us? It tells us that the indices we have over here are related to the iteration number and the row number. Because when we were in row 2, the only indices we saw were iteration 1, 1, and 2. When we go to row 3 in iteration 1, the only indices that we are using here are 3 and 1. And so we can say that the Gaussian factor is computed by A, which is the matrix, A what? A row iteration divided by A iteration. So row is J, iteration is I, divided by A iteration, and that gives us this. So we have row iteration, look at that, row 2 iteration 1 divided by iteration 1, row 3 iteration 1, row 3 iteration 1 divided by iteration 1, and then we have row 2 iteration 1 divided by iteration 1. And so we can say that the general formula for finding the Gaussian factor is A row iteration divided by iteration. And that is our Gaussian factor. The next is to write these particular operations that we were writing as a certain row, a certain new form of A, which is the new form of the row, is equal to the old form of the matrix minus the Gaussian factor times the row that we were dealing with previously. And this is what we're going to fill next time. Let me pause here for the next for us to continue later next time. Thank you. Ajay?